So since we have seen what a perceptron is is a very, very simplified model of a single neuron, right? Of a single neuron. So people said if single neuron, and we know perceptron is very, very similar to logistic regression in some ways, right? It is related to logistic regression. We saw it diagrammatically in the previous video. So we know logistic regression is a very interesting and certainly a very powerful technique. And we studied that in full detail in a chapter called logistic regression. Now, what is the extension to this? So people said, how does a single neuron look like? You have a bunch of inputs, right? And you have an output. You have your yi hat here. You have your xi1, xi2, xi3, so on and so forth, xid, right? So this is what a simple perceptron here is. There is a function here. If the function is a sigmoid function, you get logistic regression. If the activation function, which is here, if it is a simple perceptron thresholding function, you get a perceptron, right? This is what it is. It's a single neuron. At the end of the day, it's a very, very simple. It's a single neuron, right? It's a single neuron model. So people said, what if instead of a single neuron, I have a bunch of connected neurons or a network connected neurons, connected like a network. That's where you get the name neural networks, because it's a network of neurons, right? So people started coming up with some simple ideas like this. Imagine if these are my inputs, right? If this is my xi1, this is my xi2, this is my xi3, and let's say this is my xi4. People said, what if instead of a single neuron, I have multiple neurons here? So people said, what if these inputs go here? Similarly, these inputs also go to the second neuron, right? Similarly, each of these inputs also go to my third neuron. And from here, let's assume the outputs of these neurons, let's assume are connected to other neurons, right? So here the output, see, all these edges are only going forward. So all these edges are like this. There are no edges that are backward. All edges are directed forward, right? All edges, even though I'm not drawing all of them, all edges are only forward edges, right? So now let's say the output of these neurons, if I connect it to one more neuron, right? And let's assume this is my yi hat, right? So this is called a neural network because we have a network of neurons now. Again, let's look at the terminology. This is called the input layer, right? This is called the input layer. We have seen this. This is called this is the output, right? This is the output, and this layer is called the output layer. This layer is called the output layer. Now these layers which are in between your input and output are called hidden layers. They are called hidden layers. Okay, because they are hidden between input and output. In a simple perceptron, you basically have an input layer and an output layer and nothing else in between, right? That's what we've seen in a single perceptron, right? You have your input layer here and you have your output layer here. That's it. There are no hidden layers in a simple perceptron or a single neuron model, which is a perceptron, or even in logistic regression. If you try to represent logistic regression as a neural model, what you have is a simple input output without anything else in between, right? In a neural network, this is a neural network. A neural network, or it's also often referred to as multi-layered perceptron, because there are multiple layers here and each of these could be thought of as perceptrons. Again, you will have some functions here. They could be the same function or different function. There are functions being applied here, right? So these are called hidden layers. And for simplicity, let's call this layer 1, right? And let's call this layer 2. This is your input layer, output layer, and this is the output that you get. So this is the structure of a simple multi-layered perceptron or a neural network, right? So that's what I mean when I say MLPs or neural networks. Having learned this, the big question right now, the major question right now here is, why should we care about multi-layered perceptrons? Why should we care about them? We know that we should care about these simple models because they're like logistic regression, and we've seen that logistic regression works fairly well. Is there any reasoning why we should care about networks of neurons like in a multi-layered perceptron? There are two arguments to that. The first argument is a biological inspiration. So when neurologists or neuroscientists, right, in neuroscience, when people started dissecting brains of humans, dead humans, of course, humans, rats, and monkeys, they realized that the neural structure within the brain of humans, rats, monkeys, even ants are actually connections of lots of neurons interconnected in very, very complex ways. There are lots of neurons. There are millions, even billions of neurons. There are millions of neurons interconnected in very, very smart ways. So they said, since our basic neuron, remember, our basic perceptron, was inspired from a neuron, they said, what if we can represent the neural structure, right? This connected structure or network that exists in a human brain or a rat brain or a monkey brain. So there was a biological inspiration that if a single neuron is powerful, an interconnected set of neurons must be really, really powerful. Now the big question is, how do you connect it and how do you make it work? That's a big question. It took almost decades of work, multiple decades of work to make these complex neural networks or MLPs work. We'll come to that later. But there is a biological inspiration behind it. There is also a nice mathematical argument, very interesting mathematical argument, actually very, very simple mathematical argument. Okay, so to understand this mathematical argument, we'll divert slightly from the core discussion, and I'll explain this with an example. So let's take a regression problem. Let's take a problem of regression. What is a problem of regression? You're given x, you're given xi's and yi's in your data set, right? This is your data set, and you have to determine a function, let's say capital F, that connects your xi's with yi's. Right? This is the task of regression, right? You want to find a function capital F, right, that relates xi's with yi's. That's a problem of regression. Again, here your yi's belong to real values in a regression problem. So let's take regression for simplicity because it's easier to understand regression than classification for this argument, right? So let's assume I'm given this data set where this is my x-axis, right, and this is my y-axis. Okay, so I'm given, let's say, some data set, xi comma yi, right? Let's assume xi is just one-dimensional data, okay, r power 1, and yi anyway is simply r. So this is one-dimensional data where my data is also one-dimensional. So if you want to look at it tabularly, you have your xi's and yi's like this. This is your data set. So I just did a plot of xi's and yi's, just a simple scatter plot, let's say, okay, or a line plot. Let's assume when I plot my xi's and yi's from my data set, it looks like this, right? It looks like this. Now my question here is, given this data set where this is x-axis and this is y-axis, what is my task in regression? My task in regression is to find f, which connects my xi's to yi's. This is the task of regression. And when I plot it, it looks like this. It's one-dimensional data, right? So it's very, very easy to plot. Now my question is, how do I come up with this function? Okay, let's take case 1. If my case 1 was f of xi equals to xi. So if I say yi equals to xi, how will this plot look like? The plot will look like this, a 45-degree line. Of course, some points are closer to this, but there are lots of points where the error is a lot. So your function has to be far more complex than a simple line, right? If I were to plot a simple line, if I'm doing a simple linear regression, right? If I were doing a simple linear regression on yi and xi, okay, probably the line that I'll get will look like this if I'm doing a simple linear regression, or maybe not exactly that. Maybe it will look like this. Okay, let me draw it. I think the line will look somewhat like this if I do a linear regression on my data set xi, yi. Okay, but linear regression is not sufficient because you see there are xi yi pairs of points here, even here, etc., etc. Right? So what do I do? Simple linear regression is not working. Of course, you can go to random forest, all of those things. But let's try to write it in a functional form. We want to find the capital F, which connects xi and yi. Now, let's say, okay, as you can see, I actually plotted this function. The capital F here capital f of x is 2 times sine of x square plus square root of 5x. This is the actual function from which I plotted this. You can see here, right? This is the graph of 2 sine x square plus square root of 5x. It's a very, very complex function of x. Okay, so there is a trigonometric function, there is a square root function, there is a square, there is a multiplication, there is an addition. There are lots of functions here. So let's try to understand why multi-layered perceptrons are powerful from this example of a regression problem, right? So let's go step by step. So let's assume I have a function f1, which is an addition function, which is an add function. Let's assume I have a function f2, which is a square, compute the square of a number, okay, x square or 5 square, whatever number you give. Let's assume my function f3 is a square root function. Let's say my function f4 is a trigonometric sine function. Let's say my f5 is a multiplication function, right? Now using these functions, can I construct this larger function? I can. So let's see how to do that, right? So imagine if I have x here as my input, 5 also as my input, right? I can first multiply x and 5. I can have a multiplicative unit here. I can have a multiplicative unit here. So what is the output of this? 5x, right? So if x goes inside this and 5 goes inside it, the output is 5x, right? The output here is 5x. Okay, let me not put it in, let me just write that in a different color. The output here is 5x, right? Similarly, I can take my x, okay? Similarly, I can use the function square and I can input x to this. When I input x to this, what do I get? What is my output here? My output here is x squared, right? So what is the function that we have? We have 2 times sine x square plus square root of 5x. Now I can construct this complex function. This is a very complex function, right? This is a very complex function, but I can construct this complex function using a multi-layered perceptron-like structure, right? So here I have x square. What is the next operation? Let's say I do sine of this. What do I get now? My output here is sine of x square. Is sine of x square. Okay. Now I can also input 2 here and pass both of them to a multiplication function here. What is the output here? What is the output that I get here? The output that I get here is 2 times sine x, sorry, let me change the color here. The output that I get here is 2 times sine of x square. I have my 5x here, right? So now if I pass my 5x through a square root function, what do I get? The output that I'll get here is square root of 5x, right? Now if I take this output and this output, right? This output and this output, and if I pass it through an addition symbol, addition function, what do I get here finally? Okay, what is 2 sine x square, right? We have the 2 sine x square here, 2 sine x square plus, because it's an addition, no? So 2 sine x square is coming from here, and here what are we getting? Plus square root of 5x, plus square root of 5x, and we're adding both of them. So this is my, now this is my yi hat. So we have seen that if each of these, remember, look at this multi-layered perceptron. What do I have? I have some inputs here, right? I'm passing these inputs through a sequence of functions, right? If my functions here were sine, multiplication, square root, etc., if they were, I could have written this complex capital Fx. What was my capital Fx here? My capital Fx was, right, my big capital Fx is 2 times sine x square, 2 times sine x square plus square root of 5x. Right? This is my function. And now I can represent this function using a multi-layered perceptron-like structure. This is not exactly a multi-layered perceptron, it's a multi-layered perceptron-like structure where you have these multiple layers, right? So this is your input layer here. Okay, let me change the colors here. This is your input layer. This is your, this is your output. This is your output layer. This is your input layer. This is your output layer. Okay, this is the output, and all these are hidden units now. So by having this multi-layered structure, this is important. By using a multi-layered structure, right? Structure, we can come up with, we can arrive at, or we can come up with complex mathematical functions, to solve our problem. So here it's a simple regression problem, right? So for regression problem, instead of just having a simple function, if you have a, if your data set was like this, if your data set was generated from this function, what would you do? Having this multi-layered structure gives you enormous power, right? Enormous power, because you can come up with complex mathematical functions to solve your problem, to solve your regression problem in this case, right? So the multi-layered perceptron structure, right? The multi-layered structure gives you enormous power to your models, right? Because look at it, a simple linear model, if you recall our discussion about complexity of models and about overfitting and underfitting, a linear model is the simplest model. Right? If your data is non-linear, right, like this is not a linear data at all, right? Having access to more powerful models or more powerful class of functions certainly enables you to solve much harder problems. Your linear regression is a simple linear model. Similarly, your logistic regression is a simple linear model for classification. Having nonlinear models, we discussed about nonlinearity and how to create nonlinearity using radial basis functions or RBF based SVMs. We've seen this, right? Even random forests and all decision trees or GBDTs can create nonlinearity. Here we are creating nonlinearity through a sequence of functions, by applying a sequence of functions, which is very powerful. Now, equally importantly, this is very similar to the concept that we learned probably in our high school. If some of you have forgotten, let me remind you what it is. It is called function composition. Some of you may recall these as f of g of x or g of f of x. Some of you have forgotten this. So basically what this means is, right, if you can represent this is called function composition. Literally what it means is, let's take our problem, right? What is our problem here? 2 times sine x square plus square root of 5x. This is our capital Fx, no? Now this capital Fx can be written as, okay, if you recall these functions that we had here, you can write the capital F in terms of F1, F2, F3, F4, F5. Right? You can write it like this. Okay. Let's see the steps for it. Okay. You can write capital. So how can we write this? We can write this as, okay, what is our multiplication function? Our multiplication. So let's take step by step. Let's write 2 times sine x square. Okay. Going back to this, just keep this in reference. What is our multiplication? F5. Okay, this is nothing but f5 of 2 comma sine. So f5 is multiplication. It's a multiplication of 2 and sine of x square. And what is sine function here? Sine function here is f4, right? So f4 of x square. Now I need square function. What is square? f2, right? So I'll do f2 of x. This is equivalent to this. What is square root of 5x equivalent to? Square root of 5x is equivalent to f3 of f5 of x comma 5. Now what is capital F of x? Capital of f of x is what is add function now? Add function is F1. Add function here is F1, right? So let's go to F1. It is F1 of, okay, F5 of 2 comma F4 of F2 of X comma, because this part is this part is here, this part is here, F3 of F5 of X comma 5. So what you have is F1 of F5 of something, which is nothing but f of g of x, no? What is f of g of x? It's f of g of x. What is g of f of x? It is g of f of x. So what is your capital F, capital Fx? Capital Fx is f1 of f5 of 2 comma f4 of f2 of x and f3 of f5 of x comma 5. So this is nothing but your multi-layered perceptron, mathematically speaking, is nothing but function composition that we all learned in high school, which is nothing but your f of g of x and g of f of x. So your multi-layered perceptron, in a nutshell, multi-layered perceptron is basically a graphical way, of representing simple function composition, f of g of x, for f of g or g of f of x type of concepts. But it's done graphically. And it is powerful because, as we have seen here, you can represent very, very complex functions like this by using function composition. This is one of the most important ideas of whole of neural networks and deep learning. The key idea is that having a multi-layered structure results in very, very powerful models. But just a small caveat here, very, very important point. Multi-layered structure results in very, very powerful models. But since you have very powerful models, you can also overfit very easily. We'll understand the overfitting and underfitting later in this chapter. But because since we already know overfitting, bias, variance, all of this, I thought I'll make a point here. Powerful models, while they can represent very, very complex things, they can also easily overfit. So you have to be careful about overfitting, right? And the whole task in neural networks and deep learning is to avoid overfitting. That's one of the biggest challenges. And the multi-layered structure is one of the most important and interesting and most powerful ideas in whole of modern deep learning and probably in the whole of machine learning itself.